Hello everyone. Today we are going to discuss a different kind of simple harmonic oscillator, something known as a torsion pendulum. Now here's a little diagram of a torsion pendulum. You have a wire, all right, suspended here, and then in this case we've got a disc attached to that wire. Now, unlike, say, a pendulum that would swing back and forth or a mass on the end of a spring that bounces up and down, this rotates. So if this is the equilibrium position, this is just where it sits. If I took that and moved it to one side, right, it would twist the wire, and the wire would twist back, making it oscillate. So it would go back and forth, right, rotating back and forth. You imagine that? Couldn't find a good video on this, so just have to imagine this rotating back and forth. Okay? Now, if we were to graph the angular position, right, of this, we would see something here kind of interesting. Right? We would see that the angular position as a function of time is sinusoidal. And therefore, it's a simple harmonic oscillator, right? Just like the mass on the end of a spring. Except we call this one an angular simple harmonic oscillator, right? Because it twists and turns, if you will. It doesn't move up and down or right and left or linearly like a mass on the end of a spring. We call that a linear simple harmonic oscillator. This is an angular simple harmonic oscillator. Now it's going to be very similar to the mass on the end of a spring, except as always with rotation, a little bit harder, right? We have to be a little bit more complex. If you remember here, the period of a mass on the end of a spring depended on a couple of things. Right? It depended on the mass that you had attached to the spring, and it depended on the spring constant, right? How springy the spring is. Well, an angular simple harmonic oscillator works in a similar way, as you're going to see here. Okay, first off, this would be the function we would use to describe the angular position. Right? Notice we're using theta. Theta sub m is the amplitude again, right? But it's how far from the equilibrium position it moves, the maximum distance from equilibrium position, although, again, it's an angular position, right? Omega is still the angular frequency, t is still the time, and phi is still the phase angle or phase constant, where you start from, basically, right? So notice this is the cosine function that we use for simple harmonic motion. If we take two derivatives, we can get the acceleration function. Except this is an angular position, so we won't get linear acceleration, we'll get angular acceleration. Alpha. This is an alpha, not an A. Right? We take two derivatives. Each time we got to pull an omega out. Derivative of a cosine is a negative sine. Derivative of a sine is a cosine. So we get negative omega squared theta sub m cosine omega t plus phi. And I hope you remember the calc here. If not, you have to go back to the other video to kind of go through it. Note that we have what we called theta as part of this angular acceleration. Here's theta sub m cosine of omega t plus phi. So if we just replace that with theta, we get that the angular acceleration is negative omega squared theta. Remember that this theta is a very loaded theta, right? It means theta sub m cosine of omega t plus phi. Again, completely analogous to the mass on the end of a spring, where our angular frequency was negative omega squared x, and x was a function of time of x sub m cosine of omega t plus phi. And I know I'm going through this kind of quick. That's because it really is very analogous to mass on a spring, except twisting, right, instead of moving linearly. Okay? Now, with a spring, of course, the important thing about a spring, if it's going to be a linear simple harmonic oscillator, was Hooke's law, right? That the force exerted by a spring is equal to negative kx, where k is the spring constant, and x is how much it's stretched or compressed. Well, you might not be surprised to find that a wire can work in a similar way, except we're talking about twistiness here instead of strength of the spring. Right? So if we did a little lab on twisting a wire, okay, we would find that the torque that it applies, and if you twist a wire, it has a tendency to apply a torque to twist back to where it started from, is equal to negative, this is a Greek letter kappa, times theta. Now let me explain what kappa is. Kappa is the torsion constant. Lowercase k is the spring constant, mass on the end of a spring. Kappa is the torsion constant for a torsion pendulum. And it literally means how twisty the wire is. Okay? Some wires, because of what they're made out of or maybe how thick they are, would have a bigger torsion constant. That means if you rotate it a little bit, it'll apply larger forces, larger torques, right? Maybe a wire that's made out of something that's very malleable, or maybe it's thin, would be easy to twist and have a small torsion constant. Okay? Again, completely analogous to what we do with mass on the end of a spring. And notice here the negative means that the torque that's applied by the wire and the angular position of this disc, right, are proportional to one another but opposite in direction. This is what we would call a restoring torque. Right? When you move it a little bit here in the positive direction, the torque from the wire would tend to want to push it back towards equilibrium. If we go to the negative side here, the torque from the wire would want to push it back towards the middle, towards equilibrium. Remember, you need to have restoring torques, or in linear cases, restoring forces, for something to be a simple harmonic oscillator. So, keeping that in mind, we can do a little proof here of the period of a torsion pendulum. You're going to see a very similar equation to what we got in mass on the end of a spring, but with some rotational twists to it. That's a fun. So, sum of the torques, of course, equals I alpha. This is Newton's second law that would apply here, right? This is the torque applied by the net torque applied by the wire to the disc. This I is the rotational inertia of the disc about the axis of rotation. And alpha is the angular acceleration. Now you'll notice right away that we're not using mass because this is a rotational thing. We're using rotational inertia. And of course that comes with all of the difficulties and things that we learned about rotational inertias. It doesn't have to be a disc. This could be a rod. Okay, it could be a little barbell shape. It could be, any number of things really. You could put a sphere at the bottom of this and twist the sphere and it would twist back, right? You just need to know what the rotational inertia is, and we know many of those through many axes. Right? So in this case, there's only one torque acting on the disc, and that's coming from the wire. And as we talked about here, the torque due to the wire is equal to negative kappa theta, where kappa, again, is the torsion constant, how twisty the wire is. On the other hand, as we showed earlier, the angular acceleration, that can be plugged in there. The angular acceleration is given by negative omega squared theta. But be careful. That'll get plugged in here, but remember, both of these are very loaded thetas. Because this is an oscillation, these thetas are functions of time. What functions of time, you say? Well, theta m cosine of omega t plus phi, functions of time. They're simple harmonic oscillators, so they follow that same pattern. Plugging these two things in, we get negative kappa theta equals the rotational inertia times negative omega squared theta, and what do you notice? Well, the negatives cancel, but what else? The thetas cancel. Now be careful here, because this is a loaded theta, this tells us a couple of things. First off, the amplitude canceled out of the problem. So that means the amplitude is not going to affect the period of the torsion pendulum, right? Much like the amplitude did not affect a mass on the end of a spring. Why? Well, because a bigger amplitude will mean bigger torques, but a bigger amplitude a bigger torque, which will result in a bigger angular acceleration, but a bigger amplitude also means more distance to cover to oscillate back and forth. But it can cover that distance because it's accelerating faster. Right? And the math here, the physics, shows that it cancels out. But also notice here that the t cancels out. Right? So this is no longer a function of time. This equation that we have here is not a function of time. If we solve for the angular frequency, right, so basically we divide by I and take a square root, right, we get the angular frequency of a torsion pendulum is the square root of kappa over the rotational inertia. You might remember that the angular frequency of the mass on the end of a spring is the square root of k over m, right? The spring constant over the mass. Right? So now we have torsion constant over rotational inertia. But as I said, I want to find an equation for the period. So you might remember that the angular frequency can be written as 2 pi over the period. Right? Angular frequency is 2 pi is one complete oscillation, right? 2 pi radians technically, and t is the period. That's the time for one complete oscillation. Right? So you get 2 pi over the period. Plug that in. We get 2 pi over the period equals the square root of kappa over the rotational inertia. Solve for t, and here is our equation for the period of a torsion pendulum. 2 pi square root of I over kappa. Note again, complete analogy with the mass on the end of a spring, but rotating, right? It's an angular simple harmonic oscillator instead of moving linearly. You still get that 2 pi square root kind of formula, right? Format, and you get I over kappa instead of m over k, like it was for the spring constant. So really, I mean, it's the same equation basically, but converted into rotational quantities. Just like with the mass on the end of a spring, there's an element of inertia, obviously in the I, right? And there's an element of springiness or twistiness in kappa. Remember that the only thing that makes this, or can make this a little more difficult than the mass on the end of a spring is I, right? But you got to be a little careful of what is the rotational inertia. But again, we spent a lot of time deriving expressions for the rotational inertias of all sorts of objects we could attach to a wire. And we could even attach them at different places on the object, you know, attached to a wire, because we always have the parallel axis theorem to allow us to calculate the rotational inertia about any axis parallel to one through the center of mass. So now it's just a little short worksheet to practice using this equation and the idea of a torsion pendulum.